All right. So good morning and welcome to another optimization lecture. Today we're continuing with where we left off, which was chapter 2 of the book Numerical Optimization by Nocedal and Wright. So as the recap, we are on chapter 2 of the book Numerical Optimization by Nocedal and Wright. All right. So where we left off last time was that we were talking about optimality conditions. So this is the chapter that contains this chapter is fundamentals of unconstrained optimization. And so what we did last time is we wrote out an example of an unconstrained optimization problem that was basically like just a data fitting problem. And we said how this is an example of something you might actually want to do that corresponds to unconstrained optimization. You're trying to find the parameters of a model that cause it to fit your data as closely as possible. Then we went through and said, okay, let's do some terminology. We have different types of definitions of different minimizers. So we said there's a definition for something being a global minimizer, local minimizer, strict local minimizer, and isolated local minimizer. Then we started looking at the concept of saying, okay, how does someone even solve an optimization problem? Even say we just want a local solution, like we just want something better than all its neighbors. In that case, how do you even do it? You would think you might need to go through and check all the points in like every single possible values of the decision variables that could be true. And then when you find some that are better than all their neighbors, then you say, okay, I guess that's the local minimum. But that would be very inefficient. And so the field of optimization is about trying to find algorithms that do better than just trying every single point. And the way that a way that algorithms can do better when you have smooth functions, so if you have an unconstrained minimization problem and your objective function is continuously differentiable, and in particular also there's things about if it's twice continuously differentiable, then you're able to use certain conditions in Taylor's theorem to be able to prove certain other things hold that we call first and second order necessary or sufficient conditions. So just as the brief recap, what was Taylor's theorem? So Taylor's theorem, and again, we took this at its face value, where we said, the book says, go look at your calculus textbook and find this there. So I'm going to take that at face value. But here's what this is, and this was the basis for all the proofs last time. It was suppose that f, which is our objective function, maps from r to the n to r, is continuously differentiable. And that p in r to the n, so this is some vector p, then we have that there's this relationship f of your vector x plus this other vector p is equal to f of x plus del f of x plus tp transpose p for some t contained in 0 to 1 open. On the last video, I think on the slides that got posted, it showed 0 to 1 closed, but I made a little note in the video that says, oh, it should be open like this, but hopefully people saw that. So moreover, if f is twice continuously differentiable, . we have that del f of x plus b equals del f of x plus the integral from 0 to 1 of del squared f of x plus t p p dt. And one more, and also that f of x plus p equals f of x plus del f of x transpose p plus 1/2 p transpose del squared f of x plus tp p for some t contained in, again, 0 to 1 open. Same note from the last one that I wrote it closed on the slides, but I tried to make that note that said it should be open. Here you see it open. So this is the theorem that the reason this was important is because it is very helpful for the proofs of some of the conditions for optimization. So remember again that we're looking at unconstrained optimization. And we are in particular looking at cases where we are considering that our objective function is smooth. So as you can see here, we want it to be continuously differentiable. And if it's also twice continuously differentiable, we can have even more things hold. So if it's continuously differentiable objective function, then we know that this relationship holds true with some p and some t. And then if f is twice continuously differentiable, then we have some more properties. And so these led to the necessary conditions. So we have the necessary conditions for optimality, first and second order. So this is optimization theory, which in the end leads to algorithms. But so the necessary conditions come from when you say, okay, if x star is a local minimizer, then tell me what needs to happen about the first and second derivatives of this function. So there's first order necessary and second order necessary conditions. And so just as the recap, what were these? So the first order necessary condition is that if x star is a local minimizer, it's always so hard to write I's with this, and f is continuously differentiable, in an open neighborhood of x star, then del f of x star equals 0. Sorry, I wish it doesn't do that. All these stray marks. So as a reminder, so what this says is it says that if x star is a local minimizer, so you already know that part, and also if your objective function is continuously differentiable in an open neighborhood of the optimum, then, let's try this again. Then del f of x star is equal to 0. This really is not working out. So that tells you that you need to have your gradient equal 0 at the local minimizer. It does not tell you that just because the gradient is 0 that it's a local minimizer. That is that is not what it says. What it says is if it's a local minimizer, then this is true. So this on its own is not enough to prove that it's a local minimizer. But if it is a local minimizer, this is one of the things that has to be true. So then the way that the proofs went for this was related to proof by contradiction. So it would say, suppose that this does not hold true at the local minimizer. Then they went through and were able to use properties of continuity as well as this Taylor's theorem and demonstrate that if this is not 0, that then X star could not be a local minimizer. So then we have the next thing, which is the second order necessary conditions. So this is also what we went through last time. So second order necessary conditions. Okay, so if X star is a local minimizer of F and del squared F exists and is continuous, in an open neighborhood of X star, then del F of X star equals 0 and del squared F of X star is positive semi-definite. So we went through this one last time too. So it says if X star is a local minimizer, and if its first and second derivatives, or the gradients, if you have this function f and it's a function of many variables, then you have to have the derivatives with respect to all of the variables exist and be continuous in an open neighborhood of X star. Then del F of X star is 0. So this is what we just set up here. Has to meet the first order necessary condition, and also the Hessian, which is the matrix that comes from doing the first the gradient and then taking the derivatives from the gradient, is positive semi-definite. And we went through what the definition of that was last time. It's related to that if you have a matrix, then it's positive semi-definite if you can do something like PB or P transpose BP is greater than or equal to 0 for all P in R to the N, then you say that this B is positive semi-definite. And so again, the proof by this was also by contradiction, where it said, okay, suppose that this is not true, that it's not positive semi-definite, then we demonstrate that it couldn't have been X star as a local minimizer, so therefore it must be positive semi-definite. So what we did next is we went to the sufficient conditions. So this is first and second order necessary, where they say if X star is a minimizer, these things must hold. That doesn't mean that just because they hold that necessarily you have a minimizer or a local minimizer. So then we wanted to do the sufficient conditions, which are ones that go the opposite direction, and they say if this thing holds true, now it is a local minimizer of a certain type. So these are the sufficient conditions. And so where we left off last time was with the second order sufficient condition. and its proof. So the second order sufficient condition which is suppose that del squared f is continuous in an open neighborhood of x star, and that del f of x star is equal to 0, and del squared f of x star is positive definite. Then x star is a strict local minimizer of f. So what this says is it says, say you already know the properties of f, and that you find some point where del f of x star is 0 and del squared f of x star is positive definite when you have a function that has a continuous, like Hessian. So all its second derivatives are continuous. Then x star is a local minimizer of f. So you can start seeing how these might help with algorithms by looking at this and saying like, wow, if I knew that I was giving myself a, if I was given an optimization problem, I knew my objective function had this continuous second derivatives, and in the domain I'm looking at, then the interesting thing would be that then I would already know that if I find the point where this and this are true, it's a strict local minimizer. So you can see how this might even relate to, maybe I check this and this at different points, and if I find points where both are true, I already know this is true. So you can see how this starts to build toward algorithms, and that these things can be used in helping with that. So note though that this says it is a strict local minimizer, which is not what the first and second order necessary say. We just talk about a local minimizer. Here it says you can actually tell it's a strict local minimizer. But also note that these second order sufficient conditions are not necessary conditions. So what that means is that you can have a point x star that is a strict local minimizer of f, but does not necessarily satisfy all of the sufficient conditions. So because in the sense of like this says it's positive definite, right? So that's more than was said over here. Over here it said if it is a local minimizer, del squared f of x star is positive semi-definite. So it could be semi-definite, doesn't have to be positive definite. Over here it says if you actually go as far as to say del squared f of x star is positive definite, then you know it's a strict local minimizer. But if you only know that this is positive semi-definite, that's not what this says. It doesn't then say it's a strict local minimizer. It doesn't say it's a, it doesn't go that direction. So you can actually have points x star where you might have, for example, here's f of x star, or f of x is x to the 4th. And we could look at this point, x star equals 0. We know this is a strict local minimizer here, actually. And, but despite that this is a strict local minimizer, the Hessian actually would be 0. at this point. So that would not meet this requirement where it says del squared f of x star needs to be positive definite and then it's a strict local minimizer. It doesn't go the opposite direction. It doesn't mean just because this is not positive definite, like if it's positive semi-definite, it does not mean that you necessarily do not have a strict local minimizer. It's just saying if these hold, then you get a strict local minimizer, but there could be strict local minimizers that don't satisfy these requirements. Now, of course, they have to satisfy the necessary conditions, right? So if it's a local minimizer, del squared f of x star has to be positive semi-definite. But it doesn't necessarily have to be positive definite to get a strict one. So that's the idea here. So these are the things that 100% you need. If it's a local minimizer and you find del f of x star is not 0, you would say it's not a minimizer. If you say, is this a minimizer? And you say del f of x star is not 0, this says is 0, equals 0, not is not equal. And del squared f of x star is not positive semi-definite, and it's a local minimizer, and f and del squared f exist and are continuous, then you would say, well, then it's not a local minimizer. Then just because the Hessian is not positive definite does not necessarily mean it's not a strict local minimizer. So those are the way that that kind of works. So there's some nice stuff if you actually have a convex optimization problem. So again, the reason that this theory is important is because it leads to algorithms. So we're going to talk about then as like narrowing down and saying like, well, what if I have functions of even more special classes, and then I could make maybe algorithms especially for those types of functions. And one type of functions with a nice property that we're going to say now is a convex function. And then so those actually do have their own classes of algorithms. So when we have a convex function, here's another theorem. So if your objective function is a convex function, when f is convex, any local minimizer x star is a global minimizer of f if in addition f is differentiable then any stationary point x star is a global minimizer of f. So this is pretty powerful. It says that if you have a convex function as your objective function in unconstrained optimization, then if you find a local minimum, you also have found the global min. That's really powerful. And in addition, if your objective function is differentiable, then any stationary point, so that's where del f of x star is equal to 0, is a global minimizer of f. Wow, also really powerful, because we said over here that this del f of x star is equal to 0. This was a necessary condition, but wasn't sufficient. But over here, we're able to say that if f is differentiable, then any stationary point where del f of x star is equal to 0 is a global minimizer of f. So that's really powerful. That can be proved, but I'm going to keep going on for today. So there should be a quick note about what happens when you don't have continuity of the objective function in some way. Are there ways people have developed to handle that? And the answer is yes, people do have algorithms for trying to handle things like that. It does certainly make things more challenging. Because, for example, when you do have a smooth objective function, some of the benefits is that then you know that stuff that's true at one point will be not a sudden jump at the next point you could look at. So you sort of have a local knowledge of the function by looking at its value at a certain point. And if something is discontinuous, you might not have as much information anymore. But people do have algorithms for trying to deal with different types of these issues. And another interesting thing is that there are some functions that are not differentiable, but that you can actually reformulate the optimization problem to be, if you have, for example, f of x is equal to the one norm of some function. So it turns out that you can actually go through and write this unconstrained minimization as a constrained optimization problem, but with a smooth objective function. So this one has a non-differentiable objective function, but you can rewrite the problem through a creative sort of change of the way that you put it on paper, so that now it's a constrained optimization problem, but has a smooth objective function. So that's just some things that happen out there. But in this book, they really focus on the case that that you already have your optimization problem in a form where the objective function and the constraints, or sorry, where the objective function is differentiable. And so we're going to assume that either we're only focusing on those and that we kind of let other books deal with the cases with the non-smooth objective functions, or that we're able to rewrite it and that we already have rewritten something that might be non-smooth in a smooth form. So what we're going to do now is talk a little bit about the basics of how algorithms work. So now that you know a little bit of theory, we can talk about how does someone design an optimization algorithm so that, like we started with, you don't have to test every single point under the sun in order to be sure that you found a local minimizer. Or, yeah. So there have been a lot of developments in algorithms for unconstrained optimization of functions that are twice continuously differentiable. But the way that these work is that they are iterative. So you need to give an initial guess So these are going to be algorithms for unconstrained minimization. Of twice continuously differentiable objective functions. Because these algorithms are iterative, the basic way they work is that you start with a guess of the optimal values of the decision variables. And then after you make that guess, the algorithm generates a sequence of new guesses and stops after it meets some termination condition. And so how do algorithms determine and generate this sequence? Generally, that involves using information about the function at a given iteration, maybe also some information about the function at prior iterations. And then the goal is to find, in general, points that will lower the value of the objective function if you're doing minimization. And then because in general, algorithms are going to do local minimization, your initial guess does matter. So if you choose a point that's really close to one local minimum, you might find one. If you choose a guess close to another, you could find another local minimum. So you want to make a good initial guess that you think is relatively near the one that you would be trying to find, even though, of course, like, how does someone say that, right? I mean, you don't know what it is. How can you make a guess close to it? But of course, you can definitely, or maybe not definitely, but sometimes you can rule out regions of the decision variables that you would say, those don't make any sense, or I don't want something near those at all. And then that can help you make an initial guess, but it's hard to guarantee what will happen. But in terms of how does it generate new guesses, so there's two general ways that these algorithms will update your current guess to a new guess. And these two, which are what we're going to talk about next, are line search and trust region methods. So we'll start with the line search strategy and say, okay, how does this basically work? And again, the details of exactly how all of these things are done are part of what distinguishes one algorithm from another. But here we're going to say, what is the basic principle of line search in general and the basic principle of trust region in general? And then, of course, people can do all different types of things that sort of build on these concepts. So we're going to start here with the line search. So in the line search method, the optimization algorithm is going to choose a direction which we'll call here PK, and search along that direction. I'm just copying this from the book for a second, we can talk about it. And search along this direction from the current iterate or guess xk to a new iterate with a lower value of the objective function. And so let me just finish showing what this looks like, and then I will go ahead and describe it better. So the distance you would move along this direction, PK, is not clear just from reading this, because it says search along this direction. So you start at some initial iterate, you choose some direction to say, okay, I'm going to try to change my value of xk. So I'm going to make a new point, xk plus alpha pk. This is the meaning of the direction, is that you're going to make a new guess. So you want to choose some vector to add to the current vector of decision variables so that you can update the vector of the decision variables to something else. And this alpha here is something that then you say, how far along this direction PK do I search? So is alpha a small number? Is alpha a large number? And that sort of determines the amount that you move in this direction PK. So then the question becomes, how do I know what my alpha is? And so one idea is to solve a one-dimensional minimization problem. Where you would try to find a good alpha. So find an alpha that's positive such that f of my current xk plus alpha pk gets minimized. So I'm searching, in this case, for an alpha that, based on the direction I chose, makes the new value of f as small as possible, because I'm trying to find some point that minimizes f. Because that is the whole point of doing the minimization here of f at all. So if you do it this way, then for your given PK, you do find like the very best way to decrease f from your current point and in the direction PK that you've chosen with some alpha. So it would be like the very best way to select alpha to find the best iterate you can given this strategy. And then, but oftentimes you don't really have to do this to really get an exact minimization. Is like a minimization in a minimization. So it could take more time, and usually you don't really need to do that. It doesn't have to be so exact. It's just the next iteration in an overarching optimization problem that's trying to minimize the value of f overall. So instead, usually the line search will not do something like this. It will do some type of thing that's intended to meet this spirit, but not exactly this. So maybe it will, for example, make a number of several step lengths and try them, and then say, okay, that one looks the most minimum of the ones I tried, or things like that. So that gives the spirit, though, of what line search is. It's that you're trying to update your iterates over time to find those which you hope are making f smaller and smaller over time, so that you hope you're converging to a local minimum by having an algorithm that updates your guess of what the optimal solution might be according to this type of strategy, or, like we said, a variant of it that doesn't do a straight up minimization right here. Okay, so trust region. What's a trust region? So trust region is another general kind of concept for updating the iterations or updating the guesses that you have. So in the trust region, you're going to get a model function mk. This is the first step that you need to have. You need to have a model function, which we'll call here mk. There's a k because you could update the model as well at different iterates. So this is supposedly a function with behavior near the current point . xk that is similar to that of the actual objective function f. So what would that even kind of mean? So one idea is to use some type of quadratic function. So one idea is something like mk at a point xk plus p is equal to fk plus p transpose del fk plus 1/2 p transpose bk p. And then this will be the function value. So f evaluated at xk, and this one would be like del f evaluated at xk. And then this one can be some Hessian or approximation of it. At xk. And then, so the goal of using this type of function would be that mk and f are in agreement to first order at the current iterate xk. So that's the idea, and that shows you what this means, that you start with some model function, and that's some function that you can choose that has behavior near the current point that's similar to that of the actual objective function. What would that even look like? A possible idea is to try this idea where maybe you take some sort of like first few terms of your, or sorry, like first order approximation according to this of your function at the current iterate and use that in helping you approximate what the value of your objective function is, something like that. So that though just shows like you start with your model function. So what good does that do you? So what do you use it for? So then this model might not fully represent your actual function everywhere. So what you do then is you look for a minimizer in some region around the current iterate where you think your function, or you think this model function hopefully does a relatively okay job of representing the actual. So you're going to look for a minimizer of mk in some region around xk. So here it's going to be, again, how to get this p. So you want to find a new point, but here instead of choosing the alpha, we want to choose p. So we're going to choose our search direction by doing something along the lines of minimize p over this xk plus p, or mk of xk plus p. So find the value of p that makes this approximate function mk at xk plus p be as low as it can be, but that we're not going to allow ourselves to look at every single point ever. We're going to look at xk plus p in the trust region, which is a narrowed down region around the current iterate in order to help us hope that this approximation of the function around the current iterate is still okay within the trust region. So then if you try this out, so then you see how it does. See how your P does at decreasing F. Whoa, what's that? Okay. So see how your P does at decreasing F. And then one of two things can happen. Either you're happy or you're not happy. So say you're not happy. So if you're happy, great. If you're happy, great. If not, then the reason that you probably are unhappy is because you don't feel like your P decreased the F very much. So if that's true, if they didn't decrease the F very much, then you might think, well, maybe the reason is because maybe my MK wasn't accurate enough in my trust region so that I got a P that didn't really actually make my F get much smaller. So then you say, well, maybe the issue is that I have too big of a trust region. Maybe I'm looking at MK being too inaccurate. That probably happens if my trust region's too big. So then you can shrink your trust region and try again. Other typical things, so typical trust regions are something like the 2 norm of P is less than or equal to this big delta. And delta greater than 0 is what they call the trust region radius. But there's also other types of trust regions. The book says elliptical, box-shaped could also be used. And so so as a note, like what's the difference then? What is a difference between line search and trust region? Well, in the line search, you have this direction. And so as you're trying to figure out what's a good, what's a good new iterate, you're changing the alpha, but the direction that you're going here isn't changing. So the PK is like you add some vector and you're adding scalar multiples of that vector. And you're trying to find what scalar multiple to add to your original iterate. Versus here, when you're doing actually more of a minimization, here we're not changing an alpha. We didn't choose the original direction. We instead just said, okay, I'm going to minimize this in the trust region. And so if I do this thing where, okay, shrink my trust region and try again, which you can think of as sort of being like the concept of try different alphas and see which one is the best. Here I'm sort of trying different P's and sometimes trying actually different trust region sizes also and see which one is the best. Then when I do that, I actually could change the direction of the P. So the P is not in a fixed direction because it's just whichever one makes this function as minimum as possible. And then if I shrink the trust region, so I shrink the region I'm looking at, this function might be now minimized in a different direction. So that's a difference between the line search and the trust region. And then, so in the book, it says the line search and the trust region approaches differ in the order in which they choose the direction and the distance of the move to the next iterate. So it says that in the line search, you start by saying, I fix the PK, and then I find this good alpha that takes me to a good overall total, xk plus alpha pk. Then in the trust region, instead, they say, okay, the maximum distance I'm willing to go is within this trust region. And then it says, what's a good direction if I'm willing to go that distance? And so now we can talk a little bit about search directions in the line search. So that's probably something you've been wondering, like, okay, great, that PK thing. So where am I getting that from? Like, just out of my head, I just choose any random number, or is there some strategy? So there is some strategy. So here's concepts in search directions for line search. Which I think we can call, where is PK coming from? In a line search. So there's this concept of what is called a steepest descent direction, which is one idea for using to get PK. The steepest descent direction, negative del fk. And so I don't find this, like, when I look at that, I'm like, why is that the steepest descent? And so the concept of that would be the direction along which f decreases most rapidly. But I do not find that obvious at all. So then where the book goes with this is they say, okay, I'm gonna show you. This is the direction it decreases most rapidly, and we're gonna use Taylor's theorem again. So going back to Taylor's theorem briefly. Oh, there we go. Here's Taylor's theorem. We're going to be able to use this, and we're going to look at a case where we say that the P is going to be like an alpha P. So this P is any P in R to the N. If I call it alpha P, that's just like renaming this. Like, instead of calling it P, calling it alpha P, that's totally fine. So in this case, we can say with the Taylor's theorem, we have that f of xk plus alpha p, because again, remember that we are definitely looking at cases where Taylor's theorem holds. We're looking at cases where we have twice continuously differentiable objective functions, is equal to f of xk plus alpha p. So remember, we're putting alpha p in place of the p's that were in the original. Del fk plus 1/2. We have alpha squared that comes from that we used alpha p. P transpose del squared f of xk plus tp, and then p for some t in 0 to alpha open. So you can verify if you want to that this works out, because here we're doing f at this original point and del f at that original point, and then f of xk plus tp, where t here is between 0 to alpha. So that's like saying it's t alpha p, where the t is between 0 to 1, because it's just sort of, it's moving the alpha into the t. And so if you come back here, you can see that that's what we have down here. So it says f of x plus alpha b equals f evaluated at the x, which ours was xk, del f transpose then the alpha p, and then 1/2 it's p transpose, and then this plus tp times p, and this t has to be in 0 to 1. So if we say it's in 0 to alpha, it's like we move the alpha into the t. So you can see that that's what they're using. They're using this and saying that this is true because Taylor's theorem says. Okay, so here we are. So then the next thing that it says, and this should be related to directional derivatives, which maybe we can talk about that next, after I talk about this, after I finish this small part here. So let's just take this for granted right now. The book says that the rate of change in f along the direction p at xk is the coefficient of alpha, which is p transpose del fk. So how do we know that? Let's take this for granted for a bit, and then we can come back to this after we look at directional derivatives and then say, okay, that's what's going on. So right now, just believe the book that this makes sense. But so if this is true, that the rate of change of f along the direction p at xk is the coefficient of alpha, then the unit direction, note that they say here the unit direction, so it will be the direction where the norm of p is equal to 1. The unit direction of most rapid decrease is the p that solves this. So the minimum p of p transpose del f k such that the p is equal to 1. So like they're saying here, again, this is just a straight copy from the book, but like right here, the unit direction of most rapid decrease would be the one that causes the p transpose del fk to be as small as it can be, in subject to it being a unit direction. So then that says that since p transpose del fk is equal to the norm of p, the norm of del fk cos theta, that's just using properties of the dot product, because p transpose del fk is the dot product, is equal to del fk cos theta, because the norm of p is 1, it's a unit direction. And then theta here is the angle between p and del fk. Then you will get, because your theta is then between like -1 and 1, because that's the only values that, or sorry, cos theta, it will be between -1 and 1, because that's the only values you can possibly get. So then the way then to make this as small as possible is to get cos theta is -1 and say like, okay, the smallest possible value of this is at negative del fk, which happens when cos theta is -1. And then so then the p is going to equal negative del fk over the norm of del fk. So this says that the unit direction of the most rapid decrease is the one that causes this function to be as small as possible. And then so that happens when the P is such that the P transpose del fk is negative del fk norm. And then you use that in getting this final P. So I'll just go really quick to the directional derivatives and we can come back to this one, the statements after we look at the directional derivatives. I don't even know if I'll get as far as the directional derivatives because I think I only have a little bit more time. So we might have to come back to this at the next class. But there's some stuff at the end of this book where it goes through some very nice math reviews on a variety of different topics. And so what we're going to try to look at now is what it says about different types of derivatives, because these directional derivatives keep coming up when doing optimization. So it's good to be like, okay, how are these similar and different from the usual ways that we think of derivatives? And so I don't know if I'll get through all of this. I think I only have like maybe 15 more minutes. So, but we can start this and then we can always finish all this next time. So there's some section in Appendix 2 on derivatives. It's very nice. And so it's really nice because it breaks it down starting from what we probably mostly think of as derivatives, which again, I'm just going to copy straight from here. So let phi map from R to R be a real valued function of a real variable and the first derivative of that function at a point alpha, which we call as d phi over d alpha, is equal to the limit, and this is just the definition of a derivative as epsilon goes to 0 of phi of alpha plus epsilon minus phi of alpha over epsilon. So here we go. This is our this is what we typically think of when someone says, oh, I want the derivative at a point. Here they're kind of doing it, they're kind of using the alpha sort of like x, but then if you actually know the value of x, you would consider this to be the derivative at a point, like a certain value of the x. So the limit as epsilon goes to 0 of phi of alpha plus epsilon minus phi of alpha over epsilon. But note, so some things, even though we often think of this, note that this takes a real number to a real number. So this does not say anything about a vector. This says it's for real numbers to real numbers. So, and then the second derivative will be really similar, where you would do like, you would plug in the first derivative here, the first derivative here, and you could look at a similar thing. So then again, with scalar valued functions, then we have our familiar chain rule. So we will say that the chain rule which is for functions where you can say that like phi is a function of alpha, but alpha is actually a function of another variable, beta. So phi is still a function of alpha, but also alpha is a function of beta. So that means that as beta changes, phi is going to change. So the chain rule is d phi alpha of beta over d beta is equal to d phi d alpha over d beta equals phi prime of alpha, alpha prime of beta. So then we can say, okay, great, so far doing so good. That's back to the old calculus, but that was only like single variable comes in and a single variable goes out of my function. So that's a very restrictive class of functions I'm looking at, only the ones that are for a single real number to a single real number. So now let's broaden it a little. Now we're going to look at another one. Now we're going to say, okay, let me look at a case where I'm going to throw in a little bit of some vectors, but not for the output, just for the input of the function. I'm going to allow it to be not a vector valued function. It's still scalar valued as the output of the function, but I'll allow it to take a vector as an input. So the book calls this a real valued function. Of n independent variables. So now we've got our x equals x1, x2, dot, 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 xn transpose. And so now we can say, okay, in this case, what is differentiability? So what is the definition of a derivative when I have a function mapping multiple independent variables into a single number? And so now we're going to define this type of differentiability. This is the definition of Fréchet differentiability. So for the Fréchet differentiability, we say that f is differentiable at x if there exists a vector g in R to the n such that the limit as y goes to 0 of f of x plus y minus f of x minus g transpose y over the norm of y is equal to 0, where the norm is any vector norm of y. And we'll make a definition of a gradient. So the gradient of f at x is a g satisfying that equation. And we call that g equals del f of x is equal to partial derivative of f with respect to x1 dot 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 partial derivative of f with respect to xn. And so the way that we define those is df over dxi equals the limit as epsilon goes to 0 of f of x1 dot 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 xi minus 1 xi plus epsilon xi plus 1 dot 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 xn minus, and this is all in the numerator, f of x1 dot 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 xi minus 1 xi plus 1 dot 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 xn. Oh, sorry, it should be just over this part, over epsilon. Yeah. And then which is equal to f of x plus epsilon ei minus f of x over epsilon. With the limit as epsilon goes to 0. And then, so this is like the formal definition for how do you write something, like when you do this, it kind of makes sense to say like, oh, okay, like, yeah, as epsilon goes to 0, I get this. But then I think, at least for me, I've done this before in a calculus class where I say, this is the gradient. And I knew that this is sort of how you would represent the derivative with respect to each xi, but I think that this is fascinating in saying this is Freset differentiability, where the gradient actually has like a very specific definition here, that it happens that it works out this way, I guess, but the actual definition of this whole function being differentiable at x is that there exists some vector g that makes this happen, and apparently that g is this one. So that's kind of fascinating to learn that. So I think what I'm going to do at this point